We've learned what a derivative is. We've learned how to find derivatives, both using the limit method and also now using some of the properties of derivatives. A lot easier to do it that way. And now we're going to find some applications of the derivative, and we're going to look at the sine and cosine function as well. First thing I want to talk about finding the slope of a graph or a plot and discuss what that means. Now, right now, we talk about slopes of lines. We discuss the slopes of lines. We don't talk about the slopes of a graph, but graphs have slope. I want you to take a look at this graph for a moment here. Now, if I said, can you tell me the slope of the graph here at x equals c? How can I tell you slope when it's not a line? Lines have slope. Graphs don't have slope. Well, graphs actually do have slope, but the slope keeps changing on us. And the slope has to be looked at locally. So take a look at x equals c. In fact, I'm going to zoom in on it. And the more I zoom in, the more it kind of looks like a line. In fact, we'll zoom in very tightly, and now it really looks like a line. What's the slope of that as a line? Well, the slope of the graph is there. And the way to pick it off is to draw a tangent line. So we're going to go here and sketch in a tangent line. Grab my ruler and balance up perfectly right there at that point. There we go. So we should get an equal amount of space on either side here to really have the tangent line. I think that's probably it right about there. So the conclusion is a relatively simple one. The conclusion is the slope of the graph of f of x locally at x equals c is f prime at c. In other words, it's the slope of the tangent line at x equals c. So here's my tangent slope here. So that's really it. Slope of a curve is the slope of a tangent line at that particular point. Now the next thing I'd like to be able to do, I'd like to be able to discover the equation of an entire tangent line. I'd like to be able to discover that equation. So first thing I'm going to do is I'm going to provide you with a curve, f of x. Let's go simple, x squared. F of x is x squared. We're very familiar with this parabola. I use it a lot. Two questions. A, what is the slope of the tangent line at x equals negative 2? That's my question for you. What is the slope of the tangent line at x equals negative 2? The second question is, when you draw tangent lines, you notice that they are not multiple lines. It's one unique line. If it's one unique line, it must have its own equation. So I want you to discover the entire equation of the tangent line. And that's what we're going to do next. First things first, let's draw our curve here. So I'm going to get our xy plane ready to go. We're going to go here to 1 and 2. Let's go across here to negative 1 and negative 2. And I think I know how high we ought to be going here. 2 squared is 4, so let's go 1, 2, 3, and 4. And let's see if we can draw, well, first of all, let's get the point, establish a point at negative 2. At negative 2, we're way up here at 4. So let's go ahead and establish our point here, right about there. Let's establish the point at negative 1, which is 1. 0 is 0, 1 squared is 1, and of course 2 squared also 4. So let's sketch it in. Curls around here. Down here it makes the bowl of the parabola. And actually 1, 1 is more like there. And up it comes. 2, 4, and you know it keeps going. Okay? First thing I'd like to do, let's draw the tangent line. Now the tangent line balances up right up here. So that's not a tangent line. That's not a tangent line. It should be very well balanced. I'm going to say it's right about here. Skims that curve just like this. Just touches it up there. Now, what can you say about this line? Number 1, negative slope. Very clear, it's decreasing as you read it from left to right. Now let's talk about the y-intercept. Y-intercept's down here somewhere. It's a negative y-intercept. So all I know is negative slope, negative y-intercept. Oh, I know one more thing. I know for a fact that the point negative 2, 4 is definitely on my line. So let's label this as x1, y1. We'll save that for later. That is a point. Problem as usual. What is the slope? Well, remember, guys, that's why we're learning calculus. The derivative knows the slope. So if f of x is x squared, we don't need the limit method because we now know the power rule. F prime, this new function, the 2 comes down. We deduct 1 from the exponent. And here's something important. This right here is not the slope of the tangent line. I have to say that again. That is not the slope of the tangent line. I find that people sometimes try to use that, and they write y equals mx plus b, right? Because that's the equation of a line. And what do they put in for m? They put that in. This is a guide to the slope of the tangent line. You need a numeric slope of a tangent line. In order to get that, tell the derivative where you are. You're at x equals minus 2. That's where you are. So what we need is an evaluation. So 2 times negative 2 is, you've got your numeric slope. It is negative 4. That does look like a negative 4 slope. It's a nice steep negative slope. Now it's time to finish up. No calculus needed, right? The slope of your line is negative 4. There is a point on your line, which is negative 2, 4. That's x1, y1. And anytime you're given a slope and you're given a point, the best form we could possibly use would be point slope form. Y minus y1 is m times x minus x1. Y minus 4 is slope negative 4, and that's x minus x1. Let's keep going. Y minus 4 is negative 4 times really x plus 2, the double negative, distributive law, because I like this in y equals mx plus b form when we finish. And last but not least, add the 4. So here's the actual equation of the tangent line itself, and everything we need is there. The slope of the tangent line is negative 4, and the y-intercept just happens to be also negative 4, mx plus b. Well, let's look at the graph one more time. Apparently, we intersect the y-axis down here. That certainly looks like negative 4 to me because look at this. This is negative 1, negative 2, negative 3, negative 4 looks perfect. So we got everything we need, and it matches the picture. It matches the graph quite well. So that's how you would discover the full equation of a tangent line. Number 1, get the slope. The derivative itself is not the slope. The derivative is a function. It's a tool to deliver slope. Don't forget to plug in your x value. Get the numerical slope first, and then you should be able to discover the equation of the tangent line. Now, one thing we could do is we could graph these two functions and then visually inspect it to see if it looks like the actual tangent line. So let's do that. So what I'm going to do here, I'm going to go to the computer, and great place to do a little bit of graphing is Wolfram Alpha. If I go to Wolfram Alpha here, I'm going to ask Wolfram Alpha to graph two curves on the same coordinate axis, and we can put it right in here. So let's say graph x squared and what else? Minus 4x minus 4. Let's see what it looks like. It should look like a tangent line. You can also certainly do this on your graphing calculator as well. So there it says plot. We're waiting for Wolfram Alpha to do its thing. And it's not doing its thing. Okay, let's try it over here. Give me 1 second here because it looks like Internet Explorer is not necessarily doing its job. So we'll try this one. I like to visually see that it looks like a tangent line, and the best way to do that is by graphing it. All right, a little slow here, but it's starting to think. There it is computing, and there we go. So not necessarily the graph that you saw. They just gave us a piece of it, but it really does look very much like a tangent line. And if we want to change our scale, I can do that. Let's say from x equals minus 3 to 3. And let's see if that looks any better. Y equals, how about minus 5 to 5? You can see very clearly, no matter how we look at this, it definitely is a tangent line, and it touches the curve right at that one point, as it should. The next function I'd like to look at, I want to look at sines and cosines. And I'm going to do this by just graphing a sine curve and graphing a cosine curve and seeing if we can infer what the derivative function might actually be. Let's take a look at a sine curve. So the sine curve, y equals sine x, looks like this. Sines like to start at 0. They go up to 1. Actually, let's break this up into some equal zones here. It reaches up to 1, goes down to 0, then down to minus 1, down here, and back to 0. And of course, that's just one cycle of the sine curve. So it looks sort of like this, heads up here, comes around the bend, heads down through here, curls around, and off it goes. It does go on forever, by the way. So a couple questions for you here. I do know the period is 2 pi, therefore this is pi over 2, and this is 3 pi over 2. And without actually knowing the derivative, I have a couple of questions. What do you think f prime would be at pi over 2? So again, this is f of x. Y equals f of x. Well, drawing a tangent line, it looks to me like f prime, the derivative, should be 0 there. What should f prime be at 3 pi over 2? Same thing, come over to 3 pi over 2, and it looks to me, that looks like another 0 to me. A couple more questions. Let's do the f prime at 0, and that would be right here. Well, maybe we don't know the slope, but it's definitely a positive slope. It's a positive slope. Ends up being slope 1. What about over here at pi? That looks like a negative slope. And finally, at 2 pi is more of a repetition of 0, so we don't have to do that one, right? Because that's just another positive 1 slope. What function would do all this for you? The function that would do all of this for you is the cosine. The cosine of 90 degrees is 0. The cosine of 270 degrees is 0. Check. Over here, the cosine of 0 is 1, positive 1. And the cosine of 180 degrees is negative 1. That's a check. That's all true, because if you look at the cosine curve, you'll see all of that. So let me break this up again to pi over 2, 3 pi over 2. And the cosine curve loves to start at 1, go to 0, down to negative 1, back to 0, and back up to 1. And don't draw that as a triangle curve. Really try to make that a nice smooth curve by sketching it in like that. And it does go on forever and ever in both directions. Well, sure enough, cosine of 0 is right there, sitting up here at 1. The cosine of 3 pi over 2, cosine of 90 pi over 2 is right there, it's 0. Cosine of 3 pi over 2 is right there, it's 0. Cosine of 0 reaches up to 1. Cosine of pi reaches down to minus 1. So what's the conclusion? The conclusion is that the derivative of the sine function must be the cosine function, actually. That's not something you can get necessarily with the limit method, although there are means of doing that. But we can infer that from what we just saw by reading the slopes of these tangent lines. What about the cosine? The derivative of the cosine. Now, we'll make the cosine a g of x function, just to make it a little different. And so what would the g prime of 0 be? What would the g prime of pi over 2? G prime of pi? G prime of 3 pi over 2. Let's see if we can evaluate those graphically. So again, I'm going to take my ruler, I'm going to go up to 0, and let's look at g prime. G prime of 0 is 0. Slope of that line is 0. What about pi over 2? Let's look at this line right here. That looks like a negative slope. It ends up, it's going to be a negative 1 slope. And what about pi? Derivative at pi is 0. And how about finally 3 pi over 2? That looks like a positive slope to me, and it ends up being positive 1. So which function would give me all of those values? Let's try sine. So g of x is the cosine function, and g prime ought to be the derivative. So I guess that's the question. Hey, maybe g prime is sine. Let's try it. G prime of 0. Are you really the sine of 0? Yes, you are. So that's looking good so far. G prime at pi over 2, which is the 90-degree angle, is that really equal to the sine of 90 degrees? Well, sine of 90 is 1. Oops. So that didn't work. So it can't be the sine, because the sine of 90 is 1, and we're saying g prime is the sine function, so we would do sine of 90, and it's getting negative 1. Here's the result. Turns out the derivative of the cosine function is not the sine curve. It's the opposite of the sine curve. So actually, put a minus sign in front of all these, and everything works just fine. Put a minus sign here, and a minus there. Now we get a match. G prime is minus 1. The negative sine of 90 is minus 1. So if we had a sine curve, like this one, and we asked the question, what do you think the sine of 30 degrees is? right here? Well, first of all, I think we know what that is. The sine of 30 better be a half. So the sine of pi over 6 is the sine of 30 degrees. That's a half. The real question, I suppose, is what is the derivative or the slope of the tangent line in that area? That would be right about here. Now, it's certainly a positive slope, but what is it? Well, the derivative of the sine function is the cosine function. Remember, derivatives themselves are not slopes. What we'd want to do, if this were f of x, we would want to sample f prime at 30 degrees and see what it is. Well, this is f prime over here, so let's sample it at 30 degrees. So the real question is, what is the cosine of 30 degrees? And from memory, I remember that one. That's a very common one. It's square root of 3 over 2, which is roughly about 0.866. So it's a positive slope, not quite 1. So we can use the derivative of sine and cosine to discover the value of the slope on those curves. Now I'm going to finish this video up with rates of change, and rates of change means speed. I talked about this a lot. Average speed requires no calculus. Average speed is really easy. You take your distance, divide by time, boom, one number. You have your average speed. What I'd like to do is work through a problem, an average speed problem, and I want to not only know the average speed, I'd like to get the instantaneous speed. So I have to make up a real problem here, a real modeled physics problem. And the problem I'm thinking about is simply dropping a ball. So what we're going to do is we're going to take a ball, just like the example in the book. This is example 9. And I'm going to drop the ball. So when you drop the ball, basically it accelerates, doesn't it? Until maybe it hits the ground. So the acceleration is naturally gravity. So when we drop the ball, the first thing is the velocity is 0. I let go, and the velocity starts to slowly increase until finally it hits the ground. So acceleration is the acceleration of gravity. And the speed is certainly not constant. The speed keeps increasing. Now, the one thing we are going to ignore is wind resistance, because wind will push back on the billiard ball and try to actually slow it down. It plays a huge role if you're a skydiver. If you jump out of an airplane, gravity's going to pull on you. You're going to accelerate, but the wind pushes back, the air pushes back, until finally the force of acceleration, the force of the wind pushing back or the air pushing back are equal, and you actually reach terminal velocity. It's about 125 miles an hour for a skydiver. So we're going to ignore that. We're going to just say that we accelerate forever. Now, somebody has cooked up a formula for the position function, and that is, for this particular billiard ball, it's minus 16t squared plus 100. And this is in feet. So apparently they start the problem off with the billiard ball 100 feet above the ground. 100 feet above the ground. So this is a position function. Now, first thing we're going to do, what is the position, and let's put of t. In other words, it's a function of time. What's the position at the very beginning of the problem? The beginning of the problem, the position is what we think it is 100 feet. That's the beginning of the problem. Here's an interesting question that we don't need calculus for. When will the ball hit the ground? Well, the ball's going to hit the ground right here when position is 0. That's when it's going to hit the ground. So let's do that. Let's set S, not t. Let's set S equal to 0. Let's solve for t. So I get 16t squared is 100. I'll divide by 16. We don't need any sophisticated calculus to do this. I am going to divide this out on my calculator, however. 100 divided by 16, just so we get it right, is 6 1/4. Now, what is the time it takes to hit the ground? Take the square root of both sides to find out. Now, whenever you take a square root, you always put a plus or minus so you get both answers. So the time it takes to hit the ground is the plus or minus the square root of 6.25, which actually ends up being 2.5. And this, by the way, is in seconds. This problem is in seconds. 2.5 seconds. Now, this is a real problem. There really doesn't make any sense to talk about a negative time. We're not able to travel backwards in time, so it's the positive one. It takes 2.5 seconds to hit the ground. So you'll notice that it did not take any calculus. It didn't take any limits to find the answer to that problem. Now, the next thing that I'm going to do is say, okay, so now you know how far it travels, 100 feet down. Now you know how long it takes, 2.5 seconds. Let's calculate the average speed. Average speed. Well, the average speed is the change in position divided by the change in time. Now, at the beginning of the problem, which is up here, the position is at 100, so 100 feet. So I would say my beginning position is 100 minus, at the end of the problem, my ending position is 0. Okay, next, time. At the beginning of the problem, I'm holding on, I'm just about ready to let go of this ball. Well, the time's 0. I haven't started the stopwatch yet, so time is 0. That's the beginning time. The ending time. When does the ball hit the ground? That takes 2.5 seconds, so my ending time is 2.5 seconds. We really have to be careful about the order that we do this in. So at 100 feet, at time equals 0. At 0 feet, time equals 2.5 seconds. So what do we get here? Now these are in feet. These are in seconds. So take a look what you got. You got 100 divided by minus 2.5. It's negative 40 feet per second. Now, while in general, when we do distances are always positive, generally. We do have a thing called directed distance, but most times distance is positive. But speeds can be negative. This average rate of change, this average speed is negative to indicate that we're going down in the y direction. So that's why it's negative. It should be negative. Now we've got our average speed. It wasn't too tough to get that average speed, minus 40 feet per second. Now that's average. It's one number for the entire trip. At the very beginning of the problem, we're going 0 meters per second. I'm still holding on. And at the very bottom, when it hits the ground, it has to be faster than 40 feet per second, because we're averaging in slow speeds at the beginning with fast speeds at the end. So I would think that if you were hit that ball with a radar gun right when it hit the ground, that would be called its instantaneous speed. I'm pretty certain it's got to be faster than 40, so that we're averaging slows with the fast to get to the 40. So that is really the last problem, and that one does require calculus. What is the instantaneous speed when the ball hits the ground? We talked about this. If this is the position function, we talked about the derivative being an instantaneous rate of change or speed. So S prime, the derivative, ought to be able to reveal to us instantaneous speed. Let's take the derivative. Now, the minus 16 isn't going anywhere, correct? It's a constant multiple, leave it alone. So let's take the derivative of t squared right there. The 2 will drop down, deduct 1 from the exponent. Now, plus the derivative of 100. Well, that's just a lone constant. The derivative of a constant is 0. So s prime is negative 32t. That's s prime. In fact, I can even give this function a new name. It's the velocity function. That's the velocity function. What is the instantaneous speed or velocity when the ball hits the ground? Just inform this function what time it is. The time where it hits the ground, we already figured that at 2.5 seconds. So we would do minus 32 times 2.5 seconds. And let's see what we get here. So 32, 2.5. So at the time, at the very instant, the very moment that this hits the ground, the ball is traveling at 80 feet per second down. That makes a lot of sense. The beginning of the problem is traveling at no speed, 0. The end of the problem is traveling at 80. You average them together. Now, that doesn't always work. Depends on the function, whether you can just take the beginning speed and the ending speed and average them together. Think about problems where maybe a vehicle is going really, really fast for most of the trip, and then for the last 2 minutes, it goes very slow. You can't just take the top speed and the bottom speed and average them. It's weighted much higher than that. Calculus will take care of that for you. It'll actually figure it out. It'll do the weighting for you. But in this one, it turned out to be quite reasonable that it hits the ground at minus 80 feet per second. One last thing to talk about. S prime. What's another way to write S prime? Remember this terminology? The D and the D. And what would we put up here? Well, we took the derivative of the S function with respect to the independent variable, the t function. It's ds dt is the derivative. And that makes a lot of sense because it's a rate of change. And here's what it says. How does position change with respect to how time changes? It's a change in position with relating to a change in time. And of course, that's speed. Change in position with related to a change in time. Not only that, look how it matches up to the average speed, which really is a fraction. Delta S over delta T is the average speed, and ds dt is the instantaneous speed. Really great connection between the average and instantaneous where you do need calculus. So please try some of those examples, and now you know why we do calculus. There's a lot of value in these derivatives. We can find the instantaneous speed, for example, and that's the speed as if you were to hit something with a radar gun, let's say, and say, how fast is it going right now? And that's what the derivative can do for us. Thanks again for your attention.